Right.
Okay. So today we're going to be covering coordinates and how coordinates can be used in geometry. So this is a method, or especially the geometry part, that some people like and some people dislike a lot, but it's a very useful method anyways. So first of all, who knows like the basics of coordinates? So we have a coordinate plane on like a grid. So who knows like what this point will be? And let's just, yes. So Jennifer says X and Y axis. So this is X, this is Y. Yeah, so, oops. Okay. Some people are saying that this is the point 2, 3. So let's just quickly go over like what this means. And other people are saying origin. So origin is this point in the middle. What? Okay. So basically the way a coordinate plane works, there's an x-axis and a y-axis, and they're perpendicular to each other, which means they form a 90-degree angle. Then the intersection is called the origin, and we write this as 0, 0. So this point would be 2, 3, because we can like go 1, 2. So the first coordinate is how far you would go right. And then the second coordinate is how far you would go up. So it's 1, 2, 3. So this point would be described as 2, 3. Does this make sense to everyone? Okay. This is something that you're going to learn in school. And yeah, I think it's covered a decent amount in school. So notice that there are actually 4 boxes. So like 1, 2, 3, 4. And those are the 4 labels. So it goes from 1, 1, 2, 3, 4. And let's look at this box. So since the x coordinate is on the left, oh yeah, they're called quadrants. I kind of forgot that. We're not going to be using polar coordinates, I think. So if we go left, then the x-axis becomes negative. So this point is negative 5, 1. Because we go 1, 2, 3. Wait, I can't count. 4, 5, 6. It's actually negative 6, 1. So, and then this point is 1 up as well. Does that make sense? Or like, does everybody understand this? Because this is what we're gonna be going off of for like the whole class. To Adam, I'm using Notability. And just one last example, this point is negative 3, negative 3, because it's both left and down. All right, so the first thing that we're going to learn about in here is the idea of slope. So let's draw another coordinate plane. This is the x-axis, that's the y-axis. So let's say we have one point at x1, y1. And the second point is at x2, y2. And we want to connect a line between them. So slope is equal to the change in y divided by the change in x. So what does this mean here? This means y2 minus y1 over x2 minus x1. in the case of this line. And people often know this as rise over run because it's the amount that you rise divided by the amount that you run, I guess, if that makes sense at all. So if we look at it visually, the slope would be this. Let's label it A, and let's label this B. It would be equal to A over B. So that's what slope is. So why is slope useful? So the reason why it's useful is that given a line, let's just draw a line here. Let's say we choose any 3 points, or any 2 points actually. A property of a line is that no matter the 2 points that you choose, the slope is always equal. So if we choose this as A and B, or we choose like C, D, the slope between AB is equal to the slope between CD. And yeah, this is the same with parallel lines, and we're going to cover this later. So there's one more coordinate plane, or actually a lot more coordinate planes. We're now going to derive the formula for a line. So the first formula that we have is called point slope form. So to make this formula, we have a point x1, y1, and we have a line passing through it, just a random line with slope m. Now, I guess an equation of a line is, so we have a point xy, and we want to be able to determine if it's on this line. So to know this, the slope between xy and x1, y1 must be equal to m, because that's the slope. So we can write the equation using the definition of slope. Y minus y1 over x minus x1 is equal to m, because m is the slope. And this is how we defined it. So multiplying both sides by x minus x1, we get y minus y1 is equal to m times x minus x1. So this is a really useful formula. So given a point and the slope, we can find a line. And Hansen already said this in the chat. So some people might be confused. What does this actually mean? So let's use like an example to try to understand this. Like you might be a bit confused about the y, x and the y, and like all that. Yeah, Hansen, we're gonna cover that after. Or he asked like, can't you also do y equals mx plus b? So let's say we have a point 1, 2. And there's a line passing through it that has slope, let's say like, the line looks like that. So the rise over run of this slope, or the rise over run of this line, is like that. So given any 2 points, let's say this point 2, 0 and 1, 2, it would, the slope, which is equal to m, it's equal to 2 minus 0 over 1 minus 2. And this is equal to 2 over negative 1. So this has slope negative 2. Then let's try to find, okay, so a lot of people are saying the slope is 2, but the slope is actually negative 2. And a way that I usually tell this is that if the line is going to the right, like to the bottom, then the slope is negative. Okay. So now we can just use point slope form. So we have the equation above. So let's just plug it in. Also, just to clarify what we're plugging in, we define x1, y1 to be equal to 1, 2. So when we plug it in, we have y minus 2 is equal to negative 2 times x minus 1. So this is the equation for this line right here. So how do we use this line? How do we use this equation? So we can tell whenever a point is on this line just by plugging it into the coordinates x, y. So let's look at this. Just by counting 1, 2, 3, 4, 5, 6, this is negative 1, 6. But usually you don't have graph paper, so it's not that easy to see that it's on the line. So let's have xy is equal to negative 1, 6. Then plugging this in here, we have 6 minus 2 is equal to negative 2 times negative 1 minus 1. So this is 4 equals negative 2 times negative 2. And this is true. So this is how we know that the point negative 1, 6 lies on that line. Okay, so we're now going to go over point slope form. Or not point slope, slope intercept form, which I think is the main other way that people determine equations. Okay, so let this point be just a random point 0, b. Ignore that it's on the third square, because that doesn't matter at all. And let this line have slope m. Using point slope form, well, let's look at point slope form again. So it's y minus y1 equals m times x minus x1. So let's write that here. Y minus y1 equals m times x minus x1. So let's plug in x1, y1 is equal to 0, b. So plugging that in here, we get y minus b is equal to m times x minus 0, which is mx. So this means y equals mx plus b. And this is called slope intercept form. And the reason why this is called slope intercept form is because this is called the y-intercept, or the point at which the line passes the y-axis. So this uses the y-intercept and the slope, and it has a really simple equation for the line. So I think this is all we have for slope intercept form. So now we're gonna just show why these lines are useful, like how we could solve an equation, or how we can find the intersection of two lines. Oh, Nathan gave an equation for the line, which is correct, but we're just using like in general. All right, so this might be a bit messy, but hopefully it's fine. That's too long. Let's have a line that passes through 0, 2 and looks like this. Wait, I can't draw, so I'm like relying on this. I messed it up. All right. So this passes through 0, 2. And let's say we know the slope is -2/3. And let's have another line that passes through 4, 4, as well as, let's say this point. Wait, no, not that point. Let's say this point. And this is -1, -4. So let's first find this line. And let's color it green, just to make it easier. So this passes through 0, 2, and has slope 3. So notice that this is the y-intercept. So basically in the equation y equals mx plus b, this b value is equal to 2, and this m value is equal to 3. So the green line is y equals 3x plus 2. Okay, this is the equation of the first line. Does this make sense to everybody? Okay, so the second line is this one. Wait, that's not spam. Spam is bad. Okay, so the second line passes through -1, 4, or -1, -4, and 4, 4. So right now we don't have a formula just to find the equation between two lines, and there isn't one that I've actually remembered. So the way we do this is we find the slope. Since we know 2 points, we can just write the slope to be 4 minus -4 over 4 minus -1. And this is just using the formula. So we have 8/5. So the slope is 8/5, and this looks relatively correct. So now what we can do is we can write the equation using point-intercept form, or point-slope form. Okay, so this using point-slope form, we have 8/5 times x plus 1 is equal to y plus 4, if we just use this equation. So this is the other. And the last step, we want to find this intersection right here. And to find that, we have a system of equations. So we have these two equations, and we want to find x, y such that both are satisfied. So let's simplify this one first, because the red one first, because it doesn't look very nice. So we multiply both sides by 5. So 8 times x plus 1 is 5 times y plus 4. And just expanding this more, we have 8x minus 5y is equal to 12. And this is the form that I actually prefer because it's just pretty nice. And it's the form that you usually see systems of equations in. So it's pretty simple to solve them. So now we can just solve the other equation. we have these two equations and we want to find x, y such that they work. So notice that the second one writes y in terms of x. So we can plug that into the first one. So 8x minus 5 times 3x plus 2 is equal to 12. And 8x minus 15x minus 10 is 12. So negative 7x is equal to 22. So x equals negative 22 over 7. So this is the first coordinate. And we want to find the second one now. So the second equation seems simpler. So let's just plug it in there. Y equals 3 times x plus 2. And this is 3 times negative 22 over 7 plus 2. And this is negative 66 over 7 plus 2, which is negative 52 over 7. Wait, I made a mistake somewhere. Wait, this is bad. I made a mistake somewhere. I think let's try solving the equation again. Wait, Eric said 2 plus or minus square root 3. But I don't think this would give like irrational coefficients or irrational values. Wait, does anybody want to try? Let's just try finding my error. Wait, actually, never mind. I'm bad. So here, I accidentally wrote the slope as 3 when it was negative 2 over 3. So here, this equation should be negative 2 over 3x plus 2. So let's just solve this equation again, I guess. So it's going to be a bit uglier this time. So let's just plug it in again. So 8x minus 5 times negative 2/3 x plus 2 is 10. Is equal to 20. So this is just computation now. And something that you'll notice with coordinate bashing is that there's just a lot of computation, which is why a lot of people dislike it. So let's just look at this coordinate to make sure it makes sense. So x equals 30 over 17. So that's between 1 and 2. And it's a lot closer to 2. So let's look at it here. And that makes a lot of sense. Okay. So now we can just plug it in to the second equation again. So those cancel. So it's just negative 20 over 17 plus 2, which is 14 over 17. So we get the intersection to be 30 over 17, 14 over 17. Wait, 17. Okay, so this is just an example of intersecting two lines. And we notice that the denominator is 17. So this is because, and that's not very nice. And it could get a lot worse because the points that I chose are pretty nice. So this is a reason why coordinate bashing isn't really common after like the AMC8 through AMY. And in Olympiads, where the problems are like a lot harder and you get hours to solve like 3 of them, there are other bash techniques that are used, like complex and Berry, and you could learn about them, but they're a lot more complicated than coordinate bashing, and they aren't going to be covered in school at all. So one last thing I'm going to talk about is parallel lines and perpendicular lines. Wait, no, there's something else, but whatever. Okay, so first of all, Charlie already defined what parallel lines are. So they're two lines that would never intersect. So consider these two. We could extend them forever, but they never meet. Yeah, Emma already said the definition in the chat. Okay, so now let's compute the slopes of these two lines, and let's see if there's any relationship we can spot. So to do this, we can just do rise over run. So rise is 1, run is 4. So the slope is 1 over 4. Similarly, let's compute it here. The rise is 1, and the run is 4. So this slope is 1 over 4 as well. And to add them, yes, the lines are parallel. So these slopes are exactly equal. And this is a really interesting and useful thing because this just shows that for two parallel lines, their slopes are equal. And similarly, let's consider two perpendicular lines. Okay, and yeah, so people are saying negative reciprocal or they multiply to -1. So let's just confirm this real quick. For 2, and for here, it's 2 over -1. Wait, yeah, this is -1. So this has slope -2. So these are negative reciprocals of each other. And you can notice -2 times 1/2 is equal to -1. So this seems like a pretty simple idea, but in reality, the proof is pretty difficult, I think. Because I don't know any other proof that doesn't involve law of cosines. And that's too hard for this class, for sure. So we're going to go over one last formula. Wait, law of cosines isn't too complicated, but it's definitely too hard for this class. Let's consider a polygon. And to make it simple, let's have a triangle at first. And let's just make up coordinates like 6, 8, 4, 19, 5, 6. That's too big. Let's say 1. Okay, so the reason why I chose these coordinates, we're going to find an area with these 3 points as the 3 vertices. So let's just first plot these to see what it looks like. This is 6, 8. This is 4, 1. and this is 5, 6. So just from plotting it, we can see that the area should be really small. But there isn't any very clear way to compute the areas. Or one method that I actually learned from school, and some of you, some of you might have seen these before, but the way that some people approach this, let's just ignore these coordinates. You draw like a rectangle around it. Then you can compute areas of these rectangles and triangles. Then just subtract it. Yes, it's the rectangle thing. And it's kind of annoying and just a lot of work. So there's a really quick formula to compute this. So let's just write the 3 coordinates again and repeat the last one. Now this is called the shoelace formula. So the reason why is because when we draw these lines, it looks like a shoelace. Pick's theorem is completely useless. So in shoelace, you multiply these along the shoelaces. So this is 6, this is 24, this is 40. And for this side, this is 32, this is 5, this is 36. So now you add these together, and on the left side, you get 73. And on the right side, I think you get 70. So the formula, you subtract these two and divide by 2. So you get the formula to be 1.5. Or you get the area to be 1.5. And that makes somewhat sense because this shape is like really thin. And shoelace can be extended to like quadrilaterals, pentagons, polygons with more sides. But the thing with that is you have to list them in either clockwise or counterclockwise order. And I think that's all we have to cover for this part. Now we're going to do some problems. And here I don't have a graph, so I'm sad. But let's just try graphing. We want to find the area of this. No, I'm not going to let you leave 30 minutes early. Okay, so the vertices are at 0, 2, at 1, 2, and let's just say this is like 5, 3. Wait, that's a very bad triangle. It's okay. Somebody said 2. Okay, so to do this, we use we use base times height over 2. So what's the base here? It's 1. And if we look at this and let's ignore that. We look at this and try to extend it, and we drop that perpendicular. This length is equal to 1 as well, because 3 minus 2 is 1. So essentially, this is a triangle with base 1 and height 1, even though it doesn't look like one. So base times height is just, over 2 is just 1/2. This can be confirmed with shoelace as well, but shoelace is a lot more work than this. Okay, we're going to go on to the next question. And this is an AMC 8 question now. So I'll just let you all read it first. All right, somebody said C. I don't know if that's the right answer. Oh, it actually is C, but I didn't give choices, so. Okay, so let's start. We first give a quick sketch of the intended solution. So the intended solution to this problem is using something called similar triangles. So I'm going to color two triangles. And we note that we haven't covered this technique, which is why I'm not going over the similar triangle solution. That's a good enough triangle. So basically, these two triangles, you can wait. Let's not search it up because that kind of defeats the whole purpose. So similar triangles are two triangles that have like the same shape, or they look like the same shape. And if some of you might know it, and you can tell that these two are similar triangles. And this is how you're supposed to solve the problem. Yes, the answer is a number. So let's just hope that we don't know. Let's just say we don't know how to do similar triangles. And let's coordinate bash. So how do we coordinate bash a geometry problem like this? Oops. So what we do is we essentially like slap a coordinate plane onto it. And this is normally built around like a central right angle. So E becomes the origin. So E is 0, 0. Then this is at 3, 0. This is at 3, 4. This is at 0, 4. And this is all stuff we can just tell from the diagram. Similarly, this is at 1, 4. This is at 2, 4. All right, Aiden asks, why are we bashing? So you definitely shouldn't bash this during the test, even though I did. But yeah, let's assume we don't know how to do similar triangles. Because bashing, basically, you don't have to think and you just do it. While similar triangles, you have to think. And thinking is bad. All right. Okay, so in order to find this point in the middle, let's call it P. So let's think about what we're going to do to solve this problem. So first step, compute P. We want to compute the coordinates of P so that we could find area of triangle CEP. And by symmetry, we can just multiply by 2. So let's do the first part first. Okay. So P is the intersection of BE and CF. But as we saw before, finding the intersection of two lines is somewhat annoying sometimes, like kind of annoying and not that nice sometimes. So let's draw this line. That's not very good. Let's draw a line that cuts this in half. Let's say this cuts the rectangle in half. So basically P passes through the center, or this line passes through the center of the rectangle. So we know the x coordinate is 1.5. So this is like exploiting symmetry. And this may feel like a fake solve, but it's not at all. So let me draw this line again, just to make it clear. Okay, so this point is like 1.50. And this basically cuts this in half. Okay. Yes, the answer is C, which is 3. But let's just go through to solve this problem. So the x coordinate is, so this is just saying like P is halfway between like E and F in terms of the x coordinate. Now we also know that P lies on BE. So let's try to find the equation for BE. So to do this, we know B equals 2, 4, E equals 0. So the slope here, the slope of BE is 4 minus 0 over 2 minus 0, which is 2. So you might remember from before the equation that we had, y equals mx plus b. This is the slope, and this is the y-intercept. And in this case, the y-intercept is just 0. So we can replace b equals 0, and m is equal to 2. So y equals 2x. And that's actually a pretty nice equation. Since we know x equals 1.5, this means y equals 3. So p equals 1.53. So let's label this on the diagram now. All right, so now let's try, now we use shoelace to compute the area of CPE. So this triangle, there isn't a very clear like base times height over 2. Oh, okay, to Aiden, I actually did coordinate bashes on a time test. And after you do a lot of like coordinate bashing, when you do it yourself, it becomes really fast. And even though it may be slower than similar triangles, this is a pretty fast way to solve this. Okay, so the three coordinates are 0, 0, 1, 4, and 1.53. So let's write it again, write 0, 0 again in the end, and draw the shoelaces. So this multiplies to 0, this is 3, this is 0, this is 0, this is 6, this is 0. So now let's subtract them and divide by 2. And the answer we get for now is 1.5. So it's easy just to stop here and say the answer is 1.5. But we notice that it says the shaded area. And that's 2 triangles. So we do 1.5 times 2 is 3. And that's the answer. And yes, people said that a lot like before, but I'm pretty sure they searched it up. All right. Let's do another question. Okay, I think this is the last question we're going to do. And then after, I'm going to do some 13, 14, 15 stuff, which you'll see. So they don't give us a diagram because they're mean. So we have to draw it now. Wait, no, I actually deleted the diagram. Whatever. So this diagram isn't great, but all right. So let's see. Okay, let's just put this on a coordinate plane now. So we have the x-axis is AD, y-axis is AB, and A is the origin. So let's put it like that. I can't draw. So let's just label some points now. This is 0, 0. This is 4, 0. This is 4, 3. This is 0, 3. Okay, so let's try to find E first. So that's the first step in this problem. So we want to find E. To find this, we want to intersect this line. We want to intersect this. Why are you? Okay. We want to intersect this line, and we want to intersect that line. Oh, you can just look at the problem. It's mostly just a diagram. Okay. So we want to find E. The first step is find AC. AC is from 0, 0 to 4, 3. And the slope of this is 3 minus 0 over 4 minus 0, which is 3 over 4. And using slope-intercept form, y equals mx plus b, we know the y-intercept is 0. So this means AC is y equals 3 over 4x. All right, so now in order to find E, we need a line passing through B perpendicular to AC. So we have a formula for this from before. So we know slope BE is a negative reciprocal, which is negative 4 over 3. So using point slope form, this passes through 0, 3. So the y-intercept is 3. And just plugging this in, we get y equals negative 4 over 3x plus 3. Wait, Jaden, that's not span. Okay, so we have these two equations, and let's solve them. So we notice that they both, oh, somebody solved it really fast. Okay, so we noticed that both of them have y in terms of x. So we write that. And to solve this, we multiply both sides by 12 because we don't like exponents. Yeah, I can go back to the problem. All right, hopefully that's enough time. You can just search up the problem to get the problem statement. Okay, so we multiply both sides by 12 times 12. So we get negative 16x plus 36 equals 9x. So negative 25x is negative 36. And we can plug this into here. So y equals 3/4 times 36 over 25. So this is 27 over 25. So we have this to be, I forgot it. Okay. 36 over 25, 27 over 25. And we notice that this isn't very nice. I mean, it's not terrible, but it isn't terribly nice as well. So one might go to use shoelace immediately, but we can notice what they're actually asking for. They're asking for the area of AED, which I'm coloring in right now. Okay, so we can use base times height over 2. So since just the definition, this is 27 over 25. And Jennifer says the base is 4, which is correct. So 4 times 27 over 25 over 2. So the answer is 54 over 25. So this was a little messy, but we still ended up getting the answer. And this was an AMC 10, number 15. And I think I coordinate batched this question during the actual test, which was probably not very smart. The other solution is using similar triangles, like Eric said in the chat. I'm actually not sure what the actual solution is, but I would assume it's using these similar triangles, or like the similar triangles around here to find some lengths, then just computing the area. But similar triangles, at least for me, are like kind of hard to find. Okay. So there are 2 more problems, which I'll send out, I guess, as challenge problems, which are kind of homework, but not really homework. So it's an AMC 10, number 22, and an AMC 10, number 19. And these are both a lot simpler. These are both a lot simpler with not coordinate batching techniques, and they're a lot faster. So I'll just say this is law of cosines, which a lot of you don't know. So we're not covering the real solution to this. And this is probably just like math. I don't know. But this is like pretty simply coordinate batched. And one last thing is like, when do we like coordinate batch? So notice that this problem, there's a rectangle. So a rectangle is very important, or something like that, because we want like a central right angle to put the axes on. And also we get like these lengths, these line intersections are like not too bad too. So this is like a problem that seems pretty easy to coordinate batch. Okay, that's it for this class.